This is a video sharing about the data development analysis method. It is also for the ER International Conference 2020. Wang Zhijie and Professor Wu Xianhua from Shanghai Maritime University, School of Economics and Management, recorded this video. So today we want to share a paper which is published on the Transportation Part D. The title is Efficiency Evaluation and PM Emission Reallocation of China Ports based on novel DA models. So firstly, let's take a look at the background of this article. As the great artery of the national economy, the waterway is the most important part of the transportation around the world, but it still can negatively impact the environment. We take the data from the International Maritime Organization. According to their report, it shows that international shipping, domestic shipping, and fishing, they are totally produce about 1.5 million tons of PM, which is 7% higher in 2011 than in 2008. This figure worried environmentalists. We know nowadays, whatever the countries, the cities, or the organizations, they are all beginning to protecting the environment. For example, to protect the environment, IMO issues a Regulation 14 beginning at the January 1st, 2020. The Regulation 14 is also known as the sulfur restrictions. It requires that the sulfur content in vessel fuel is to be abated to 0.5%. And then to China. The Chinese government also issued emission control regulations to protect the local environment, to protect the port areas. Not only in China, we found that in North American region, Baltic and North Sea region, they all have their own ECA areas. The ECA areas means the emission control areas. It requires that the vessel must burn no sulfur fuel when they enter these areas. Because of these strict rules, ports must continue to increase their investment to meet such requirements. And we know when they increase their investments, and it also will cause negatively impacting to their profits. But we believe it is a trend that the government, the society will pay more and more attention to environmental problems. So given this fact, we naturally raise a question about how much governments should limit air pollutants and what ports can do to follow a more stringent set of rules. Because we know the environmental protection is becoming more and more important today. We should not lose environmental protection because of economic development. However, in the same way, we should also not impede the pace of economic development because of the environmental protection. Regarding to this background, this paper wanna investigate the relationship between the port efficiency and environmental regulations or environmental control. In our paper, we select 11 Chinese ports, such as the Shanghai Port, Ningbo Port, Qingdao Port. These 11 ports are all listed companies in the Shanghai Stock Exchange that the data is easily obtainable. And We also classified them into 4 areas because we wanna measure the differences between the ports, deal with the environmental control individually, and the inter-port cooperation. Here in the video, we briefly presented some key findings in our paper. Firstly, in our model, we set the preferences coefficient, which also means the direction vector, here in red in our paper. So you can refer to our paper for more details for this set. So firstly, we measured these 4 areas about their technical inefficiency and environmental regulation. This picture shows that the maximum potential increasable standard container throughput for 4 areas from 2012 to 2016. As can be seen clearly that the picture A shows that area 1 and area 3. Area 1 is green line and area 3 is blue line. They have zero output to increase, which means they have higher technical efficiency. For the area 4 is the red line here. Area 4 has a slow downward trend from the beginning to the end. It reflects that it becomes more and more efficient. For the area 2, in the pink line, it is the most inefficient area in this picture A. And in picture B, C, D shows the potential increase mainly follows the direction vector of expected output. However, it is noticed that all areas follow the same trend regardless of the direction chosen by the ports. In this case, only area 1, area 1 is also the green line, has a higher technical efficiency all the time, and area 4 becomes the most inefficiency area. This picture shows that we also measure the technical inefficiency for the 4 areas under the non-environmental regulation. So this picture shows that no matter what direction areas are chosen, in order to obtain the technical efficiency, area 4 has the most potential desirable output to increase, which means it has the most technical inefficiency. Here, the area 4 is the red line. In the 4 pictures, it has the most potential increasable output. Area 1 in this picture shows that it performs well under the non-environmental regulation compared to the environmental regulation. So its technical efficiency remains unchanged in most years. The area 1 in most years, it keeps non-changed. A result can get from this picture is that few growth of areas are expected in the vertical direction. In our paper, vertical direction remains the mu equals to 0, the phi equals to 0, the mu equals to 1, the c equals to 0. The vertical direction means the picture A. So, except for the vertical direction, the picture B, C, D, all areas still follow the same trend regardless of the direction chosen by the ports. Then we can compare and calculate the output loss between the environmental regulation and the non-environmental regulation. We can see clearly that for area 4, it has a dramatic increase in an output loss before 2014, and then stays high until 2016, which implies that area 4 bears a huge loss under environmental regulations than others in any directions. One potential reason is that the port resources have not been fully developed in this area, so that resulting in technical inefficiency. In particularly, the Area 3. The Area 3 had zero output from the 2012 to 2016 in all directions, which means the Area 4 keeps the same technical inefficiency and environmental regulation and non-environmental regulation. Importantly, this picture shows that all areas have the same output loss trend no matter what direction areas chosen to respond to environmental regulation. Here, we present the two pictures. Let's see the left part firstly. The left part picture is about the potential increasable output at different PM emission targets for areas 1 to area 4. The different emission targets we use omega to stand for. When omega decrease, it means the government raised their emission standards. So we can get the result from the left part picture. Firstly is that even if stringent emission standard is in fact, almost areas still have the potential increasable desirable output as long as they are willing not to choose a vertical direction. The vertical direction is about picture A, picture E, I, and M in here, and the non-vertical direction is for the other pictures. Also, the vertical direction is A, E, I, M in this picture, and others is non-vertical direction. So back to this picture. Back to this picture. The first result is, the second result is, if the government raises the standards to promote emission reduction, all areas must abate activities to meet the pollution regulation. Third, Area 1 has zero increasable desirable output from the 2012 to the 2016 in any directions. You can see here, we cannot decrease omega. When we decrease the omega, we will get a negative value. So that it means the Area 1 has the highest technical efficiency. Last, all areas have the same trend to decrease the desirable output with stricter environmental regulation, except for the vertical direction. Let's turn to the right part. The right part shows the potential increasable output after PM reallocation. In our paper, we assume the PM reallocation could be worked in certain areas, and we call PM reallocation as a cooperation strategy, and non-PM reallocation is a non-cooperation strategy. So the red part picture shows that the potential increasable output after PM reallocation compared with the actual desirable output. It shows that with raising the emission limit by the government, areas have the same trend to reduce the desirable output in their preferred directions and values from positive to negative. For example, picture F, we can see when we decrease the omega, it means that the government raised their emission standard, and then we can find the output level will decrease also, and the value will decrease from the positive to the negative. Third result we can get from this picture is that all areas can efficiently reduce the amount of the potential desirable output in a reallocation or PM emission with more weight given to mu. However, input costs and a penalty for pollution should be taken into account in this decision. Then this picture shows about the output loss between the cooperation and the non-cooperation strategies for the 4 areas. In the vertical direction, again, vertical direction means the picture AEIM. In the vertical direction, all areas have 0 output loss because the value is the same between the cooperation strategy and non-cooperation strategy. In the other directions, output loss is foreseeable to increase in area 1, 3, and 4 in most years. We give a possible explanation about it. It is that some members may become more and more inefficient, and result in the forced improvement with cooperation. Consider for the area 2, the cooperation strategy is only valued in 2012. The maybe inefficient ports in area 2 may consider dropping out of the alliance to seek new partners, or the alliance kicks out the relatively inefficient members to optimize the sum of the standard container throughput. So the whole picture here also shows that the cooperation strategy will lose ground to its non-cooperation strategy. Which means the value of the output loss will gradually reduce to 0. For example, picture J. The cooperation strategy the value of the output loss will reduce to 0 when the omega decrease. Then we list the most important conclusions from the previous introductions here. The first is eastern ports in China. The area 1 generally have a higher technical efficiency due to the efficient production with relatively few import resources. The second is the port aliens can effectively increase the sum of desirable output under environmental regulation. Third, the port cannot accept an overly restrictive pollution emission target, no matter whether they are aligned or not. The fourth, the ports have multiple decisions to deal with the environmental regulation. Of course, there are some limitations in our paper. Firstly, it is needed to assess the multi-influenced factors such as the penalty for pollution emission and import costs. We don't include this in our paper because we cannot get this data easily from the public sources. The second is In our paper, we measure the PM emission by the top-down method. As we know, the top-down method is not always a good method to give an exact value for the emission. So in the future study, we propose to use the bottom-up approach if you can get the data. Third, the discussion on the reallocation of emission permits by the applying game theory to review the dilemma of ports, cooperation and non-cooperation strategy. Finally, we welcome you to cite our paper, criticize, and correct our paper via video, via the DEA International Conference, or the email address. That's all our presentation. Thank you.